My name is Zoe Screwala. I'm at the Hudson River Foundation. I've been helping to administer the Polgar program this year. So we have two of our 2024 Polgar Fellows, Aaron Novobilski and Dhruvi Prajapati, and we're going to listen to their presentation of findings from the research this summer. So we're really looking forward to that. And throughout their presentations, you can feel free to ask questions. We have a chat that you can send messages in, and we would love to get some questions for the fellows to discuss their findings. And I believe you can also raise your hand, and we can allow you to come and ask a question with your microphone and video if you would like to. So without further ado, I'm going to pass it over to Jonathan Kramer, president of Hudson River Foundation, to give a little introduction and welcome.
Good afternoon, everyone. I'm just so privileged to be able to say hello to you today and to kick this session off with the Polgar Fellows. For those of you who don't know anything about the foundation, I wanted to just spend just a couple minutes talking about us and the beginnings of the Polgar Fellowship Program. The foundation's been around for a very long time. We were established in 1981, and our mission is to inspire and inform action through science and engaging people, all in service of the vision of a healthy and resilient Hudson River for nature and people, flowing from its watershed through the mid-Hudson and the broad reaches of the river there to the urban estuary that we're lucky enough here at the foundation offices to have right outside our window. That over the course of our many years as a foundation, we have been able to use an endowment and to support over $40 million in research grants, but we do more than that. We have a deep commitment to engagement of managers, policymakers, researchers, and others to help them make better decisions and to learn about this remarkable resource. We manage and support research and restoration through a variety of programs, including the Champlain-Hudson Environmental Trust, Hudson River Ecosystem Monitoring Program. We're now working on sturgeon in New York Harbor and a variety of small grants programs. And we all have been for almost 10 years now the home of the New York, New Jersey Harbor and Estuary Program, a US EPA funded effort that brings federal partners together with state and local entities to really focus on this lower portion of the estuary. Along the way, over these many years, the Polgar Fellowships have been an integral part of the foundation, and we are deeply, deeply proud of the work that's been conducted under the auspices of the Polgar program. The Polgar Fellowships began in 1985 and focused for many years on a broad range of both undergraduates and master's and PhD students. And for the last several years, we've focused just on undergraduates. There have been over 300 fellows over this 40-year stretch. This is the 40th cohort of Polgar Fellows, and we've funded over $1.5 million to support this program. The goal is to provide opportunities for students to conduct scientific or public policy research on topics pertinent to the Hudson River and its watershed. An essential part of this effort has been the deep engagement of mentors who work with students to really build opportunities for young scholars to learn over the course of the summer and to do and have a genuine research experience. I would say that one of the key features of a program that's been around for such a long time is really dedication of staff and partners. Here at the foundation, folks like Helena Andraco have been really fundamental to maintaining this program. And now Zoe has played a really important role. And I can't say enough about our long-term partnership with Herner, which you'll hear about in a second, and DEC. And Sarah will talk about that. And Sarah has been involved with the program for many years, and that partnership itself has really been key to the long-term success of the Polgar Fellowships. So I'm excited to hear from the students, which we'll get to in a few minutes, but I want to turn the stage over to Sarah, who will talk a bit about Herner. And Sarah, take it away.
Yeah, thanks, John. And certainly we've loved being a part of the Fellowship Program. We've loved working with Hudson River Foundation all these years, and we've really been able to advance a lot of our research priorities by funding students to do these very important, they seem small scale little summer projects, but they're not very little when they set the stage for informing natural resource decision making and supporting larger research initiatives down the road. So I just wanted to share my screen. Let's see. Okay, are you seeing my presentation? Great. So I'm the manager of the New York State Department of Environmental Conservation's Hudson River National Estuarine Research Reserve. We're one of 30 research reserves across the country. We have a shared mission to be stewards of our nation's estuaries through education, through restoration, research and monitoring, and then providing that information to decision makers. And one of our strengths across the system is we monitor our estuaries in very similar ways so that we can see how the Hudson River estuary is doing, how resilient we are with climate change compared to other similar protected areas across the country. So HRNR is a federal program. We're funded through NOAA, and it is administered as a federal state partnership, and our state partner is the New York State Department of Environmental Conservation. We were designated in 1982, and we have 5,000 protected areas of tidal wetlands across our 4 component sites. And those are to the north, just above the city of Hudson, is Stockport Flats. The Tivoli Bays marshes are adjacent to the Bard College campus. Iona Island is part of Bear Mountain State Park, and Piermont Marsh is just south of the Mario M. Cuomo Bridge. And that picture there is our facility at the Norrie Point Environmental Center, situated at pretty much the midpoint of the estuary between our 4 component sites. So the reserve program has what we call 4 sectors. We have the research and monitoring sector, education and outreach, stewardship and restoration, and the coastal training program. So the model is we use our 4 component sites as living laboratories, collecting long-term monitoring data and providing logistical support for students and researchers to come in and conduct their own studies. Our research and monitoring program is now headed by our research coordinator, Chris Mitchell. Education and outreach focuses on high school and undergraduate level programs. We have the EEL program. We host a lot of top school and college field trips. And the education program is headed by Chris Bowser. Stewardship and restoration uses our component sites as more experimental pilot projects that then inform larger scale restorations throughout the Hudson. That program is led by Brian DeGasperis. Our coastal training program is currently vacant, but the idea with that position is to build collaborative networks, to foster collaborative research, and then to take our information and translate it for decision makers so the natural resource managers can really use it to protect the tidal wetlands. This is a bit about the monitoring program because all of our information is publicly accessible, that students like the Polgars can use this information as a baseline information for their research. We collect what we call abiotic monitoring. So that's the nutrients, water quality parameters through data sounds, meteorological data through weather stations. And then we do our biological monitoring, focusing on submerged aquatic vegetation, or SAV, and emergent tidal marsh habitats, where we're looking at both the spatial distribution and vegetation characteristics, and really thinking about with the resilience of those marshes, or if there's changeover between the types of communities with sea level rise, if the marshes are still able to provide their ecosystem services. So our monitoring data is collected from our nutrient data. We have a very large data set that goes back to 1991 from all of the reserve sites. We started collecting water quality data at Tivoli Bays in 1995. When we first moved to the Norrie Point Environmental Center, we started that station in 2007. And then over the pandemic, we reorganized some of our monitoring and added the Stockport Flats component site and then Iona Island at Bear Mountain. Our meteorological station at Tivoli Bays has been operational since 1999, and again, the Norrie Point station since 2007. And all of that data, 15-minute data back to the 1990s, is available. There's two places you can get that. We've been transmitting since 2005 through the NEAR's Centralized Data Management Office, and that's where you can access information from any of the research reserves. And we're also a part of the Hudson River Environmental Conditions Observing System Network, which is now coordinated by Brittany's mom. And that has been transmitting since 2008, and you're able to access all of our data through that website, including other partners who maintain similar stations throughout the Hudson River estuary. As far as habitat protection, we oversee the state's efforts to map the habitats, both the submerged aquatic vegetation maps and the tidal wetland maps. So the spatial ArcGIS layers are publicly available at the New York State ArcGIS Clearinghouse. So thank you, and we're so excited that we can do all of this work that gives these students information and the platform to be able to dip their toe into science, to explore their own ideas, to think scientifically and methodically, and to really advance their own careers while they're supporting the information that they give to us. So again, here's my contact information if anyone has any specific questions for me. But I am eager to hear from our students. So Zoe, I'm going to turn it back over you to facilitate the rest of that. Thank you.
Thank you, Sarah. All right, this is the main event. We're going to start with Erin Novobilski, one of our Polgar fellows who's coming from Marist College. Her project is titled Evaluating Potential Threats of Harmful Algal Blooms Associated with Beaver Dam Impoundments in the Hudson River Suburban Tributaries. And her supervisor is Zion Kloss. And just remember that you can submit questions, the Q&A, that's at the bottom of your screen, or you can raise your hand at the end and we'll get to your questions. All right, Erin, go ahead.
I'm going to share my screen. Hi everyone, my name is Erin Novobilski. I'm a junior at Marist College studying environmental science and biochemistry. My advisor is Dr. Zion Kloss, and I am evaluating potential threats of harmful algal blooms associated with beaver dam impoundments in Hudson River suburban tributaries. So to begin with some background, cyanobacteria thrive in nutrient-rich water with low turbulence, stagnant water, and a high pH. When they're able to experience excessive growth rates due to being in very favorable conditions, they can lead to harmful algal blooms, which are commonly referred to as HABs. As many as 75% of cyanobacterial blooms contain certain species of bacteria that can produce a variety of cyanotoxins, which can be very dangerous. One of these toxins is known as microcystin. They can make people or pets sick if they're swam in, and especially if they are ingested. So climate change, septic systems, and recently beaver dams are all increasing the areas in the Hudson Valley with favorable conditions for a bloom. This includes increasing nutrients and temperatures in waterways and also slowing down the flow of water. The blooms are occurring at greater frequencies, magnitudes, and durations in the Hudson Valley, making them a high point of interest for looking at and studying. These blooms prove to have a very negative impact on human health, economy, and food webs. So understanding their growth patterns and toxin potential is important. It can help with future planning processes and remediation efforts. So along with blooms, beaver populations have also grown recently in number as they have expanded in the Hudson Valley and are expected to continue growing. Beaver activity can have many positives. They're referred to as ecosystem engineers, and as the name suggests, they can really change landscapes drastically. Their actions and the dams that they create can reduce erosion and produce new habitats for small fish and other wildlife. Along with the visual landscape changes that they produce when they build, the ponds they create also lead to biogeochemical process changes. So with expanded beaver populations and then an increase in beaver ponds in the area, these changes are becoming more prevalent. Specifically, these ponds increase water storage, they slow nutrient transport, they change flow hydrology, they increase carbon and nutrient storage, and they also shorten stream reaches. They may also be the perfect breeding grounds for cyanobacteria or their dormant form known as aconites. It is possible that these could potentially travel further downstream and then bloom. So overall, there are a lot of questions about the variation that beaver dams can cause in environmental systems. These aconites that I mentioned are a form of dormant cyanobacteria cells. They're common in eutrophic lakes as organic rich sediments have been found to be important for aconite-forming cyanobacteria. They are found in sediment in unfavorable conditions, which includes factors such as too high nutrient contents or too low temperatures or not enough light, as all of these can limit cyanobacteria growth and decrease the potential for a toxic bloom. In the dormant form, they are able to travel, and they may do so until they experience a growth period under favorable conditions. In these favorable conditions is when they germinate and they use air vesicles to enter the water column. It is here where they can continue to grow and potentially produce toxins. An important characteristic of the dormant cyanobacteria is that their genomes multiply 15 times as much as the vegetative cells. They are also very resistant to environmental conditions. If they are present in beaver ponds, it may be possible that they could lead to more harmful algal blooms downstream, as they could greatly be increasing the amount of possible cyanobacteria in an area that could form a toxic bloom. Putting this background together leads to the statement that aconite growth in beaver pond sediment may be increasing the reach of a beaver dam's potential impact to further downstream and brings the focus of a beaver's impact outside of the actual beaver pond. This leads into the hypothesis for this study, which is that aconites present in beaver-formed ponds are more likely to lead to blooms with higher cyanotoxin concentration than what would otherwise be present in the streams the dams themselves replaced. A secondary hypothesis that is also evaluated is the growth rate of a bloom increases with the presence of sediment from beaver-formed ponds due to increased nutrient content compared to the rate that would otherwise occur in the stream prior to the beaver. It is necessary to evaluate the connection between beaver dams, a changing climate, and high nutrient loading to be prepared for future threats to the environment and humans' health. The climate is becoming more unpredictable, and nutrient inputs from runoff or failed septic systems are large threats. Harmful algal blooms have immense impacts on human health, the economy, and food webs as they can outcompete beneficial phytoplankton, they lower oxygen levels, and they lead to toxin buildup. Toxin buildup can cause severe illnesses to humans or pets. This study aims to understand the possible impacts of beaver dams on cyanobacteria populations and the secondary consequences of their impoundments. It also aims to assess any enhanced risk of HABs in Hudson Valley water systems, areas where nutrient loading already exists under a warming climate, and these water sources are important as they are relied on for recreation, fishing, and water sources. So this study included combined sampling from Hudson Valley field sites and laboratory work at Marist College. The beaver dams used for the study are listed as Stissing Mountain, Bulls Head Road, Cary Institute of Ecosystem Studies, Wetland Trust, and Vassar College Nature Preserve, based on the location or the ownership of the land that they were located on. At each site, sediment was sampled from the 5 beaver dams and 5 paired upstream locations that flowed into each pond. The upstream locations represent a pre-beaver pond sample and were compared in analysis to the corresponding beaver dam. Pictured are evidence of beaver seen while I was sampling. The beaver habitats, the chewed logs, and the footprints in the mud are indicators that a site has beavers actively living in it. Sampling was a very challenging but also rewarding part of my fellowship experience. It involved communicating, planning, and working in ways that I hadn't before, and it also involved meeting new people that helped me a lot with the field sites and also seeing a ton of new field sites. So once the sediment was collected, growth chambers were set up using glass beakers, the sediment, water, a heat and light source, and a nutrient medium. This was done to promote the germination and growth of cyanobacteria. Miracle-Gro was used to increase the nutrient contents in the beakers to produce favorable conditions for cyanobacteria. Miracle-Gro is an over-the-counter fertilizer brand that is common in many households and can typically be overused. When rain causes runoff from properties into waterways, Miracle-Gro is just one source of the excess nutrients that can end up in streams. So these growth chambers were created in replicates of 3 for the 5 beaver dam locations and the 5 upstream locations. A control of sterilized Hudson River water, which was also used in all the beakers, was also set up with no sediment in it. Every day, a sample was taken from the beakers and a floor probe was used to determine the concentrations of cyanobacteria. A floor probe, which is pictured in a Marist College lab, is a very sensitive instrument that determines concentrations of specific types of algae using their fluorescent fingerprints, as they all basically have slightly different colorings which can be detected. So once the concentration was at 25 micrograms per liter of cyanobacteria, which is New York's DEC's level for a confirmed bloom, then an ADA ELISA test was done for toxin concentration evaluation. Data analysis was also done to determine significant differences in cyanotoxin concentrations and the growth of cyanobacteria. So now going into the results from the study. The first results I want to highlight is the ADA ELISA test that I performed on my final samples once they reached over the 25 micrograms per liter of cyanobacteria. This process involves using a plate reader once finished with the methods of the test kit and receiving absorbance values for each sample. A 4-parameter logistic curve is then created using standards that were in the test kit and also ran on the plate, and that got their absorbance, and this curve can then be used to determine the microcystin concentrations of all the other samples. So pictured is the curve that was created using the absorbance and known microcystin concentration in parts per billion of standards that were included in the ADA ELISA test. And so using the equation for the curve, the microcystin concentration of samples of water taken from the growth chambers containing either sediment from beaver dams or an upstream location could then be determined. The concentrations determined are listed in the table as an average of the 3 replicates. 3 out of 5 locations had higher concentrations of microcystin in the corresponding beaver pond samples, but it was not found to be statistically significant using a pair t-test. There was a significant increase in microcystin concentrations in the samples compared to the Hudson River control, demonstrating that cyanobacteria did move into the water column and grow from the sediment to produce toxins. The other set of results I analyzed was the growth rates of cyanobacteria in the samples. The growth shows the exponential growth of the cyanobacteria in the growth chambers and was created using the daily floor probe data that was taken. This specific graph shows the difference in growth between the samples coming from sediment at the Old Bull's Head Beaver Pond location and the sediment from the Old Bull's Head upstream location. This exact graph was plotted for each location and was used to compare the Beaver Pond and the upstream samples. This is the same graph, but this shows Vassar College Nature Preserve. This pictures the Stissing Mountain samples. This pictures the wetland trust samples. This pictures the Cary Institute of Ecosystem Studies samples. So to recap the previous graphs, the cyanobacteria experienced exponential growth under ideal conditions. A paired t-test was performed between the growth rates determined using the equation of the curves. There was a significant difference between cyanobacteria growth rates from sediment in beaver ponds and cyanobacteria growth rates from sediment from upstream locations, with the growth rates consistently being faster for the beaver pond samples at all locations. So the null hypothesis was supported that cyanotoxin concentration was not different from the dormant cyanobacteria in beaver-formed ponds that would be present in the stream prior to the beaver dam. The potential toxin production from toxin-producing cyanobacteria is not higher from beaver dams compared to the stream reaches that they replaced. The secondary hypothesis was supported as the growth rate of a bloom did increase with the presence of sediment from beaver-formed ponds compared to the rate that would otherwise occur in the stream prior to the beaver dam. Due to the landscape and biogeochemical changes, there's an increase in nutrient storage and organic matter buildup in beaver pond sediment, which could be contributing to the faster exponential growth, along with the possibility of larger dormant cyanobacteria populations in the sediment. If beaver pond sediment moves downstream where there are ideal conditions for growth, which was mimicked in the study, the sediment could produce a bloom in a shorter amount of time than what would otherwise occur in the stream, leading to potentially increased risk of HABs downstream of a beaver dam. So to summarize what this could mean in a body of water is the beaver pond sediment characteristics could lower the length of time necessary for ideal conditions to persist in a single location until a HAB occurs. This timing for ideal conditions includes nutrient levels and sunlight, which can all be very variable with weather and other factors. A possible way that sediment from a beaver dam could be moved downstream includes a dam breach or a dam collapse. A sediment wedge is formed by increased deposition of sediment upstream of the beaver dam. And if the dam breaks, the sediment that is built up would be released downstream and therefore increase the risk of HABs downstream. So in conclusion, as climate change increases the frequency of high-intensity rain events and beaver dam complexes become more common in the area, there could be an increased risk of dam collapses and thus a greater potential for post-storm HABs if a dam collapse does occur. Future directions building off of this study could include performing the same methods with greater sample amounts in larger growth chambers. Also, the organic matter and the nutrient concentrations in the sediment in beaver ponds could be evaluated. Previous maps and locations of beaver dam breaches can be explored to examine if large sediment transports occurred or if they could potentially occur in the future. Also, genomic sequences of bacteria from HABs around the Hudson Valley could be compared to look for similarities to determine if there's any shared upstream source for the cyanobacteria that bloomed. So many people helped with this summer experience and made it successful and very rewarding. Thank you to the Hudson River Foundation for this opportunity. And thank you to Dr. Zeinkloss for your consistent advising and support throughout my entire time at Marist College and specifically this summer. Thank you, Dr. Raymond Kepner, for providing me with cyanobacteria expertise and also being available throughout the summer for any questions that I had. Thank you to the Cary Institute of Ecosystem Studies, Wetland Trust, and Vassar College for approving sample collection at beaver dams on their property. Thank you to Shannon Hickey for coming out to the field with me during the summer and also for assisting me with lab work. And a huge final thank you to my parents for also constantly supporting me through everything. And thank you all so much for joining on to listen to these presentations.
Thank you, Erin. So we do have a question from Lucas Haas. So the question is, so beaver dams are doing a service by holding back organic matter to prevent HABs downstream, correct? Does climate change increase occurrence of the HABs?
Sorry, could you repeat that question?
Yeah, so it looks like the person is asking if beaver dams are preventing HABs downstream, and there's an additional question about climate change, like asking if that increases the occurrence of HABs.
Yeah, so for beaver dams, what my study looked at was kind of a secondary consequence that could potentially increase harmful algal blooms. But in a lot of ways, beavers are really positive in an ecosystem. And one thing that has been studied in the past is the way that they do hold onto nutrients in the dam, which can prevent the nutrients from flowing downstream. So it's kind of two different areas of what could cause a harmful algal bloom that could be studied together and definitely be like grown upon in the future. And for climate change is increasing the strength of storms and like the frequency of high intensity storms that might be shorter. And so in terms of harmful algal blooms, one factor that is increasing is nutrient runoff. And when nutrient runoff from either fields or even just homes that have used fertilizer or from septic systems that overflow, all of this increases nutrients in streams that flows throughout the Hudson River and all through the Hudson River watershed, and that can help increase the growth of bacteria.
Thanks. We have another question and maybe offer of support from Ray Kepner, who says, "Great job, Erin. Do you still have any of your sediment samples? If so, we can quickly measure the OM content."
I do have my sediment samples, so sounds good.
Yeah. And I can ask the question, I guess, of your experience. What was either the most surprising, unexpected sort of result that you came across, and or your favorite part of your project?
So favorite part is probably seeing the beaver dams in person because there's just a lot more in the Hudson Valley than you realize. And so trying to get access points to them was challenging, but it is really cool to see the way that they can just move water levels very differently. So that was exciting, but also really challenging. And I think results wise, just seeing every day the different, like the cyanobacteria increasing in concentration was just kind of like, it felt good because it felt like something was happening and I was studying something.
Yeah, great. Great presentation. Do we
Thank
have any more questions? We can also, I'll look for raised hands. Just give it a minute.
May I ask a question?
Yeah.
Great job, Erin, and this is very interesting. And you mentioned the cyanobacteria grow faster than in the beaver dam as compared to the downstream environment. I wonder, when you grow the cyanobacteria, did you use the original water from these environments, or you use standardized media?
Yeah, so we use sterilized Hudson River water. So basically, Hudson River water that was boiled to kill off any original living cyanobacteria or other algae that was in it. And this was used as just a real life example of where this water would flow and the nutrients that might already be there and what could be limiting it in the actual field in the Hudson Valley.
So different bacteria, cyanobacteria grow with different sterilized water, or same one?
Wait, sorry, could you repeat that?
Did you grow these cyanobacteria from different sterilized water or from the same water?
It was all the same.
I
It was
see.
kept constant for all of them.
Cool.
Great. Well, I think it's time to move on to our next presentation. We're going to have Dhruvi Prajapati, who is coming to us from New Jersey Institute of Technology. And her project is titled Investigating FTCA Attenuation by Native Microbial Communities in the Proximity of PFAS Contaminated Sites Along the Hudson River. And her supervisor is Mangin Lee.
Okay, let me just share my screen. All right, so you should all be seeing my screen right now. Hello, everyone. I am Dhruvi Prajapati. My advisor is Dr. Mangin Lee. My mentor is Sambal Yakub, and we are from the New Jersey Institute of Technology, as Zoe mentioned. And our project today, the title changed a little bit, and you'll understand why as the project goes on, but it's called Investigating FTCA Biotransformation by amending native microbial communities in the proximity of PFAS contaminated sites along the Hudson River. So what exactly are PFAS? Well, PFAS stands for per and polyfluoroalkyl substances, and they are a class of synthetic and toxic chemicals with extreme resistance to chemical, thermal, and physical degradation, which is why they're also nicknamed forever chemicals. They are extremely difficult to degrade because they are made up of a chain of carbon-fluorine bonds, which are known to be incredibly strong. and they have been around since the 1950s, created to be used in industrial and commercial products like the ones shown in the image. Most of the products are for everyday use, and there's a notable use in nonstick products associated with food, which is due to the robust nature of PFASs being waterproof, greaseproof, and long-lasting. The persistence of and human exposure to PFAS is concerning because of the multiple adverse health effects they have been found to possess. Types of PFASs are linked to cancers, reproductive issues, thyroid disease, and other health effects as shown by the image on the left. And new research on the different ways PFASs have been found to harm the human body is constantly being published. To add, there are more than 2,067 confirmed sites of PFAS contamination in the United States alone. A majority of the sites are associated with drinking water, which is why the EPA now suggests less than 4 nanograms per liter of PFOA and PFOS in drinking water, emphasizing the need for their removal. Other significant contamination sites are industrial facilities, major airports, and military sites, which are significant to my project. As mentioned before, PFAS are a family of chemicals, meaning they have variations in chemical structure, like in length, functional group, and saturation, and therefore they exhibit a range of properties. My project focuses on a class of PFAS called fluorotelomere carboxylic acids, which I'll refer to as FTCAs. They are commonly found in firefighting foams, which are the source of PFAS contamination in military sites that have experienced historic use and/or storage of these firefighting foams. FTCAs are different from other types of PFASs you might have seen, like PFOAs, because they contain non-fluorinated alkyl carbons, which is highlighted in red and circled. 6,2-FTCA is what is focused on in this project, and it has one of these alkyl carbons. And these are significant because they have the potential for microbial attack for biodefluorination. After careful research, we have decided to focus on the part of the Hudson River in proximity to the Camp Smith Military Training Facility located in Peekskill, New York for this project. This site has a history of firefighting foam use, specifically aqueous film forming foams or AFFFs, and a maximum of 80.6 ppt of total PFAS has been found there as of 2019. The original plan consisted of collecting samples of sediment and river water at this site, as well as 1 mile upstream where no prior contamination was expected, and 1 mile downstream, which was expected to have lower PFAS concentrations than Camp Smith due to potential biotransformation of PFAS by the microbial communities. The hypothesis was that the microbial communities of this site is likely to possess the metabolic capacity to transform FTCAs. Multiple forms of analyses was used to understand what is actually happening throughout the experiment. FTCA analysis was started with using a fluoride ion selective electrode to measure fluoride release and determine if defluorination is occurring as the experiment progresses, and also to suggest a pattern of how defluorination might differ across the 3 sites. The total organic carbon content in liquid was also quantified because a reduction in carbon indicates that it is being used up in microbial activity, like potentially the biotransformation of FTCAs. And then liquid chromatography tandem mass spectrometry was used to quantify changes in concentrations of FTCAs and expected transformation products. This is a form of targeted analysis, meaning that it will only detect and quantify the products we program it to detect, even though there may be other unexpected products that form. A smaller scale pilot experiment was first performed where sampling of sediment and river water slurry at only Camp Smith was collected. There were 3 groups. The treatment group consisted of slurry and 6,2-FTCA. The live control consisted of only the slurry to monitor the background levels of FTCAs and other legacy PFAS, and the killed or abiotic control consisted of slurry that has been autoclaved to remove any bacteria in them, and then it was spiked with 6,2-FTCA to monitor changes in the 6,2-FTCA not attributed to microbial activities. The experiment lasted 12 days, with sampling at days 0, 2, 5, and 12 to be used for analysis. And DGBE, which was added to all of the groups, is a source of carbon and an electron donor found in firefighting foams to ensure that there was enough available for microbial activity. On the right, you can also see streak plates of the slurry, showing an abundance of microbes present in the slurry to potentially transform the 6,2-FTCA. This is what we found from the pilot experiment. The graph on the left shows the monitoring of total organic carbon, and you can see that there was very small decrease in inorganic carbon throughout the 12 days, indicating little microbial activity was present. And the graph on the right shows concentrations of 6,2-FTCA and its secondary products. The 6,2-FTCA stayed relatively stable throughout the entire experiment. And so from this pilot experiment, the main takeaway was that there is a lack of biotransformation of 6,2-FTCA under natural attenuation conditions. Therefore, we had to make changes to our original experiment. Our updated project consisted of only sampling the sediment and river water slurry from the Camp Smith site, since there was no biotransformation activity in the first place to compare with upstream and downstream sites. Next, instead of monitoring natural attenuation, which did not work out, we proposed to amend the slurry with substrates that have been found in the past to induce PFAS biodegradation activity in other types of studies, specifically nitrate and potato dextrose. Therefore, the new hypothesis was that the microbial communities of the site can be induced to transform 6,2-FTCA through amendment. On the right is a breakdown of the 4 treatment groups: river water, potato dextrose, nitrate, and killed control. They were all given DGBE, spiked with 4 nanograms per liter of 6,2-FTCA, and they all consisted of 3 grams of sediment with 50 milliliters of the associated liquid. In terms of methods, the following procedure was performed for the experiment. The sediment and river water slurry was collected at the site, and then it was filtered through a 2mm sieve. The sediment and river water was then allocated in bottles as per the breakdown chart in the previous slide, and each treatment was done in triplicates. The experiment was set to run for 4 weeks, and samples were taken at week 0 and once every week for a total of 5 time points. And then the same analysis as a pilot was performed on the samples taken. It's important to note, though, that the experiment is still ongoing and there is still 1 more week of sampling left, and analysis for the last 2 weeks is still pending. So moving on to the results so far. This graph shows the change in 6,2-FTCA concentration over 2 weeks of the experiment for every treatment group. The purple line shows that there was a significant decrease in 6,2-FTCA concentration in the potato dextrose group. In terms of the river water, nitrate, and kilt control groups, the 6,2-FTCA concentration remained relatively stable throughout the 2 weeks. These graphs show the different transformation products of the potato dextrose and river water groups. On the left is the potato dextrose graph, and you can see that it's basically empty, showing that despite a significant decrease in 6,2-FTCA concentration, there was no accumulation of transformation products. The river water on the right, though, showed an accumulation of 5,3-FTUCA and PFHXA products. And these graphs are for the transformation products of the nitrate and kilt control groups. In the nitrate group on the left, there is an accumulation of 5,3-FTUCA and PFHXA. And in the kilt control group on the right, there is no accumulation of any transformation products. And so the information gathered from the results was put together for the following takeaways. First is that a decrease in 6,2-FTCA by potato dextrose shows that the amendment was actually able to induce 6,2-FTCA transformation by the native microbial community. While the nitrate group also showed a slight decrease in 6,2-FTCA, the reduction was not significant. And also, the accumulation of no transformation products by the potato dextrose group and the increase in 6,2-FTCA by week 2 in the river water group indicates one of two things: that there is a presence and or production of other PFAS types not targeted in this experiment, or that the biotransformation in river water and nitrate groups is a lot slower than the potato dextrose group. Now, there are still 2 weeks of analysis left, though, to see how these trends persist or change. So future work, therefore, is to continue sampling and analysis for the 2 weeks, of course, but after that, solid phase extraction will be performed on the treatments to uncover any PFAS originally in the sediment or accumulated in the experiment, since there was suspicion that this could have occurred. To add to this analysis, an analytical instrument called the LTQ orbit trap will be introduced to identify the other potential PFAS types in the samples and that are being produced. And lastly, we want to perform 16S rRNA amplicon sequencing to identify types of bacteria within the sample groups. This can be used to determine the microbial community structures in the groups and how they might have changed throughout the length of the experiment. This will contribute to the overall goal of identifying types of native bacteria that possess the metabolic capability to tolerate or transform FTCAs. And finally, I just wanted to acknowledge and thank all of these people, my advisor, Dr. Meng-Yin Lee, my mentor, Sumbul Yakub, the rest of my lab members, and of course, the Hudson River Foundation and my fellows. Thank you all for your support and guidance in this project. I'll take any questions now.
Thank you, Juvie. Great presentation. Just give it a minute for any questions to come in, and I'll also look for if anybody wants to ask their question out loud. You can just raise your hand on the bottom of the screen. Okay, so we have a question from Lucas Haas. He says, great job. So do these bacteria recycle PFAS into non-harmful substances? Should these bacteria be reproduced and spread further in higher concentrations in their native areas?
So in terms of the scope of this project and how PFAS biodegradation work occurs in general, it's not often that a complete breakdown, complete degradation of the PFAS molecule occurs. So this is why, like, when I'm talking about the transformation products, they are oftentimes other shorter chain types of PFAS, which are still considered harmful. But if there was ever a way to achieve the complete degradation of the molecule, then yes, they would be harmful. And in terms of having the bacteria that we find could be helpful in potentially degrading them and introducing them into the environment as a remediation source, that ideally would be at a great would be great. However, there's also other implications we have to think about before we introduce higher concentrations of the bacteria into other parts of the Hudson or just in general. You have to think about like what the bacteria are, what their regular environment is, and also how they might affect the environment that you're introducing them into, because that could be harmful potentially.
Thank you. There's also a comment in the chat. Thank you for this project. We at Newburgh Clean Water Project would love to be apprised of your final findings. So if you want to share contact info or anything like that, we can stay in touch. And then you have another question as well in the Q&A. Are there currently research pathways to having the smaller PFAS fully broken down completely?
I do not know of any pathways that lead to the complete breakdown of PFAS, but I do know in previous literature work, I have seen potential pathways that people have produced based on their work.
Great. Well, I don't see any questions yet. We still have time, but I'll ask you the same question I asked Erin. What was something that was surprising or unexpected in your findings, and or something that you just found really interesting or exciting as part of your
So something that was unexpected was when we did the pilot experiment and we essentially saw no biotransformation happening. That was a kind of like pivotal point in the project, because we had to like rethink everything that we had proposed and figure out like how we could move forward and what we could do. And that's where we came in with our other previous background to kind of amend the direction of the project. And then in terms of like the most exciting thing, one was obviously seeing the potato dextrose group performing so well, but then in general, in terms of the actual experience, being able to go out to the actual like river and sample there directly was a great experience. I've never had anything like that before, and it came with its own set of challenges, but it was a wonderful experience in general.
Great, thanks. And it looks like Sarah has a question for you as well.
Yeah, thanks, Dhruvi. Yeah, I was just curious, when you were doing your sampling, you said you were also thinking of the mile upstream and the mile downstream. From your literature, is that like the range that you would expect from that site that used the firefighting foams for the impact, or because the river is tidal, would you expect that impact from the firefighting foams beyond that range or within that range?
So it was more of the title that you had mentioned. We basically wanted to have like a comparison gradient. So in an area that hadn't been impacted from the Camp Smith site, and then the Camp Smith site, and then after that, like how far down did it go, the effects, yeah.
And have you seen the difference in that, or is that still part of your analysis?
So we had ruled out doing the upstream and downstream sites because we hadn't found any biotransformation happening at the Camp Smith site, where we had expected the most of anything to have occurred.
Great, thank you.
Of course.
Great. Well, I'm not seeing any other questions, so I'll just say a big thank you to our fellows, to our advisors, and everyone involved in the Polgar program, and to all of you for coming and supporting our two great fellows this year. Yeah, thanks so much.